Hi everyone. Today we're going to look at characteristic physical properties. Now before we get into this note, I just want to give you a scenario. So imagine we're sitting in science class like the good old days, and I pull out a beaker, and in it is a clear liquid. What is that liquid? Is it water? Vinegar? Uh, Very well could be vodka or gin. Is it hydrochloric acid? So many different substances all look the same. Could be sugary water, could be salty water. What is it? Well, we can try to determine what it is by describing it physically. So it's a liquid, it's clear, it we in a science lab we're not going to taste it and we're not going to smell it. If it's hydrochloric acid or if it's bleach, we don't want to be tasting it, we don't want to be smelling it. That could have some very serious negative consequences, up to including death. So we can try to describe it. However, our physical description of it's clear, it's a liquid, blah, 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 that doesn't narrow it down. We still can't tell if it's water or if it's gin. So we can test it chemically. So if I dump, let's say, a tablespoon of baking soda into it, if it's water, nothing's going to happen. That baking soda is just going to make it all cloudy and eventually dissolve. If it's vinegar and I dump baking soda into it, we're going to have a chemical reaction and it's going to bubble all over the place. However, the same thing would happen if it was hydrochloric acid and I put baking soda into it. It would bubble all over the place as well. So we couldn't necessarily, we could start to narrow down what it is based on its chemical reaction, but uh, we can't tell definitively what it is. Not only that, but we kind of want to avoid doing chemical reactions because what if the substance that we are putting in reacts in a violent way? We get flame, we get explosion, we get something, a, a new substance, and that new substance is a poisonous gas. So obviously, testing chemically has some serious safety concerns. So we don't necessarily want to do that either. So how can we tell what this beaker of clear liquid is? So before we get into testing chemically, because that's going to be our last result, we're going to see if there are any characteristic physical properties, and that's today's lesson, today's note. So to identify an unknown liquid, one could test its chemical properties. But as I mentioned, we don't want to react unidentified substances. We could have an explosion, we could have a fire, we could have toxic fumes. So it's best to examine the physical properties. And as I mentioned, physical properties don't tell us what it is. Lots of things are clear liquids. So characteristic physical properties is a step up. And this is a physical property that is unique, just like fingerprints, to a substance. For example, pure water, just water. We know it freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So if we take this beaker of unidentified liquid and we put it into a freezer, that freezer set for 0 degrees Celsius, and it freezes, that tells us that we have pure water. If it freezes at 1 degree, that tells us it's not pure water. If it doesn't freeze until -3, that tells us it's not pure water. Might still be water, but perhaps it has some salt in it. And so its freezing point has been lowered. As well for the boiling. If it boils at 100 degrees Celsius, that's changing from a liquid into a gas, then it's likely pure water. If it's 104 degrees, well, who knows? It could be vinegar, it could be salt water, it could be something else. So characteristic physical property, though, is a physical property that is unique to a substance, that only one substance has. One of those characteristic physical properties is density. And this is a measure of how much mass is contained in a given unit. And we figured this out quite easily. We take the mass, which is the weight of the sample, and we divide it by its volume. So if you think of a sugar cube, it has a 1 centimeter by 1 centimeter by 1 centimeter measurement. It's 1 cubic centimeter. If we put it on a scale, we're going to get a mass or weight. If we divide that by the 1 cubic centimeter, we're going to get a density figure. If we were to put a piece of gold, the exact same dimensions on the scale, it's going to be much heavier, even though the volume is the same. And when we divide it up, we'll get a much different number. So people before you have already done this, and we do have density tables like you can see here. And so water has a density of 1. So if we take its weight for every cubic centimeter, water weighs 1 gram for every cubic centimeter. And as I mentioned, a cubic centimeter is the size of a sugar cube. If we took aluminum, it has a weight of 2.7 grams for every cubic centimeter. Gold, very heavy, 19.3 grams per cubic centimeter. So if we had this unidentified solid or liquid, we could calculate the density by weighing it, dividing it by its volume. And so if I'm weighing a substance and it's coming up as 19.3, that tells me I have pure gold. If it's coming up as 19.1, that's telling me that either I didn't measure it accurately enough, so maybe I only measured the weight to 2 or 3 decimal places when I should have done more, or I made a measurement mistake with the volume, or it tells me that it's not pure gold. Maybe there's a little bit of something else mixed in it, and it's bringing its density down a little bit. But it definitely points us in the right direction. And we can do the same for liquids as well. Of course, water is a liquid, and we can measure its density. In fact, we often do a lab surrounding this where I give you a bunch of unidentified substances, liquids and solids. You weigh them, you figure out the volume of them, you divide, you come to this chart, or a chart that's a little bit longer or has more substances, and you identify what those substances are. Here's kind of a neat thing, and you can do this at home with a cup. So this is just a picture of a whole bunch of substances that have all been poured into the same container. And the density of 1 is right here, water. It's this green substance. And I know water's not green, a little bit of food coloring has been added in just so you can see it better. But we can see the different densities. Things that have a greater density than water will sink. Things that have less density than water will float on water. So if we go back to our chart here, we know that wood floats until it gets so waterlogged that it might sink and its densities change. But if you throw a piece of wood into water, it will float. Reason being, its density is less. Ice, its density is less than water. So that's why ice floats. Your ice cube floats, water floats on lakes because it is less dense. Things like styrofoam, plastics. Sometimes if the plastic's density is less than 1, it will float. If its density is more than 1, it will sink. So all these things here, aluminum, lead, gold, they would all sink. And ethanol and methanol, very similar to rubbing alcohol on lamp oil. You can see that if this is water, they are floating on top of water. You want to see this without actually having to mix some things together, go grab an Italian salad dressing out of your fridge. You'll see that all the more dense spices have sunk to the bottom. The vast majority of your salad dressing is water, and so it is makes the most. And the vegetable oil on top is often floating on top, and that's why we have to give it a good stir, a good shake before we add it to get these ingredients all mixed together again, because they will separate. So you can see here dish soap, milk, maple syrup, corn syrup, honey. All these things are more dense, so they sink below. We can see that milk is less dense than maple syrup, so it's floating on top of the maple syrup. Along the side here, we have a few solid things. So a bolt, very dense, is the most dense thing here. It sinks to the bottom. Ping pong ball, not very dense at all because most of it is air, and so it's floating on top. A plastic soda cap has the same density, or roughly the same density, as rubbing alcohol, so it's floating in that stratification. Cherry tomato, a little bit more dense than water, around the same density as dish soap, so it's floating in that area as well. So as I mentioned, we do know the densities of a lot of different things. Different woods have different densities, but it's just an average piece of wood, 0.7 grams, lead, foam. So if we were to throw these 3 cubes into the water, the foam and the wood would definitely float. They are less dense. Lead would sink, is more dense. So we can, through characteristic properties, we can test different densities. So going back to my cup of water, something that I know won't react with it is milk. So theoretically, I could pour milk into it. If it's water, that milk is going to sink to the bottom. If so by adding in different things of known densities, we can begin to test for what we have. Likewise, rubbing alcohol and quite often lamp oil are clear as well. Other characteristic physical properties, we have the freezing point. So this is the temperature at which a substance changes from a liquid to a solid. Melting point, from a solid to a liquid. And just melting point and freezing point are the same temperature. So water will freeze at 0, but ice will melt at 0. It's kind of a unique temperature there. And the boiling point, the temperature at which a substance changes rapidly from liquid to gas. So the temperature for a change of state depends on its composition and structure. And the reason that identical particles of a substance always have the same size and attraction to each other, but are arranged differently from other substances. And now, as I mentioned, impure solids and liquids have different fixed points, lowering melting points and higher boiling points. So I talked to you about how if we add salt into the water, it's not pure anymore, and it is going to affect the boiling point or the freezing point, as you can see by the numbers I've provided here. And the reason for this is foreign particles change the arrangement of particles. So how does ice melt when you throw salt in? The salt particles don't allow the water particles to arrange the way they need to be in a solid form. It prevents that. So those salt particles prevent the arrangement of the water particles into becoming a solid, and so it stays in liquid form. And water is unique. So the unusual behavior of water, most substances, when you add heat, particles move faster, those particles spread out, and they take up more space. The opposite happens when a substance is cooled. And we see this all the time. We get cracks in the road. As you heat up roads, the particles will start to move faster. The particles spread out, the road expands, and we get cracks. And the way it cracks is it'll expand and push against each other, and the road will actually buckle up and crack. The opposite happens in the wintertime when it's cooled. The particles slow down, they move further apart, they contract, and we get these big cracks. Water is different. It behaves in a unique manner. And so as water freezes, the particles are further apart than in liquid state. And therefore they take up more space, they become less dense, and this is why water or ice floats. Normally the opposite would occur. And if water was like other liquids, it become denser, it would sink. And obviously this is a problem in lakes. That means the ice would sink to the bottom, basically killing all the fish and everything in the lake. So it's a good thing that it behaves in this manner, floats to the top, and everything underneath stays as it should be. That is it. Have a great day, everyone.